Okay, so those who were there in the last class, so they know that we started DNA cryptography, and I gave couple of background, some background on basically DNA computing, because that is required, how the initial DNA cryptography progressed, to understand that thing. Now, so let me start from where we left last time. Okay, so again, I'm just stressing that if you have not done cryptography course, you can look at these lectures to recall what is there in cryptography, because now we are mainly doing DNA security. Okay, so as I mentioned, after the first experiment of DNA computing that was done by Edelman in a seminal paper in 1994, where he solved an instance of Hamiltonian path problem using a bunch of DNA molecules. So in that experiment, he has taken each vertex as a random DNA string of certain size, say of an even length, and you divide, and then you describe the path half, and do the computation. Anyway, so after the Edelman experiment, as I mentioned, Eric Winfree uh, took the hardware from NetSiemen lab, okay, about different kind of things. NetSiemen used to do a lot of experimental stuff, like creating DNA cube and other kind of stuff. He has created double crossover DNA molecule, triple crossover DNA molecule, and using these molecules, he has created a lot of interesting stuff. So by the way, so now using these molecules, Eric Winfree has shown that you can actually do universal computation. So let me show you some of that stuff now. So the first idea is about Wang tiles. So I'm again recapturing what was Wang tile. So there are these tiles, and you can do any computation using these tiles. So two tiles can come together. For example, this tile and this tile can come together, and they will combine if the corresponding edge color matches. Okay, so this tile and this tile can combine, whereas second row, third tile and fourth tile cannot combine because the colors are different. Okay, whereas this tile and this tile can combine because the colors are matching. Similarly, if you take this tile, like this is what, second row, fourth tile, and the first row, fourth tile. So they can combine because their top color matches, right? So like that, as long as colors are matching, actually the two tiles can come together. If the colors are not matching, then they cannot come together. So this, Wang has shown that you can actually simulate Turing machine using this kind of behavior. So basically, it's a full-fledged computer sitting there. You can do any computation with a bunch of tiles. Assumption is that you should not rotate the tiles, because if you rotate the tiles, there will be a problem, right? So it has to be in the one frame of reference. Okay. So this paper is pretty thick, actually, something around maybe 60, 70 pages, where he has shown that how to build Turing machine out of these tiles. If you want, you can search on the Google, you will find that paper, Wang tile tiling system, right? There is one book also on the tilings and patterns. Title is Tilings and Patterns. There is a book which is also interesting. So I think some of you might be knowing about Penrose tiling. Have you heard of Penrose? Roser Penrose, he's a Nobel laureate. So he has done a lot of, so there are certain tiles he designed which are known as Penrose tilings. There's a lot of interesting stuff there in tiles business. Anyway, so Winfree proposed molecular weighing tiles using the branch DNA construction of cement. So, a specific kind of molecule, especially Winfree used DX molecule, which are known as double crossover molecule, and TX molecule, triple crossover molecule. I will show you a structure of one. Of course, if you want, more details are available in our last year class, on natural computing. But anyway, some of the basic I'm going to cover anyway. So now, so Winfree has shown in his thesis, you can look at that algorithmic assembly of DNA can perform universal computation using what is known as block cellular automata. I'm sure you might have not heard about block cellular automata. From the last, I don't know whether you have done a course on theory of computation or models of computation, but before that, in my discrete math lectures, I talked about 4 kind of machines, right? Finite automata, push-down automata, then linear bounded automata, and Turing machine. So those 4. So actually, Winfree has shown that you can actually, do all kind of these computation with these different DNA hardware. Change the hardware, and you can do one. You can perform computation which can be accepted by one of the machines. So basically, it's a very beautiful connection, beautiful Winfree result. It's all available in his thesis. But he used BCA. What is BCA? So I should tell you. What is cellular automata? Cellular automata is a very beautiful thing. I think, as you know, there is a nice book, New Kind of Science, by, who is the founder of, by the way, Mathematica? Anyone? Who is founder of Mathematica? Have you heard Mathematica software? It's not a competitive programming software, so obviously you might have not heard, right? So, but if you have an iPhone and you are actually, using Siri, so Siri or any this personal assistant, so the queries are actually coming from Wolfram research engine. So for example, he has written the software where you can actually do even integration, differentiation. It's a very powerful thing. So Wolfram Alpha. Okay. So so Wolfram has actually, while doing his PhD, actually, he got interest into this. He had interest in physics, and he finished his PhD at quite early, I think, from Caltech, if I remember it correctly. But anyway, so now, so he actually tried to, and that's the reason actually even he was studying cellular automata. So in cellular automata, you can see there is a cell, say one-dimensional cell, right? So there are a lot of cells inside one-dimensional tape, okay? And then you apply certain functions on the tape, and you get an output. So there is an input on the tape, and output is again on the tape using certain functions. So these functions are the ones which determines the behavior of the cellular automata. Okay. So normally you take two, so content of the two cells from the tape, and you determine the third content, in the next tape. So basically, a function could be function of 0, 1 is 1. Okay. So 0 taking from one cell, 1 taking from other cell, and then output is 1. Or 0, 0, 0. It could be anything. So it depends on what kind of function you design. So cellular automata is very, very powerful thing. And I think there was one very popular game also, Game of Life by John H. Conway. And Wolfram has written this book, New Kind of Science, to show that in nature, everywhere cellular automata is used actually. So it's powerful in biology. It has been used in, for example, modeling the traffic dynamics and so on, a lot of things. Out of those cellular automata business, one cellular automata is known as block cellular automata. So in block cellular automata, what happens? The update on the tape happens in two steps. There is one-dimensional tape with certain content inside it. Then so the cell update happens. So in even step, so basically in step one, you look at the even position values, and at the the second step, you look at the odd position values and take the function and give you the next value. Okay, so it's a two-step function. So it is known that one-dimensional blocks cellular automata is as is as good as Turing. So it's a Turing universal. So basically, that power is there in terms of computing power. That's why easy. So basically, Winfree has taken one-dimensional BCA and mapped it to the tile business. Actually, so he created this so tile computation mapped to the one-dimensional BCA, right? So let me show you how these tiles corresponds to functional molecule in DNA. So here is a double crossover molecule. You can see that, right? So there is one DNA strand, another is DNA strand, and there are a couple of other DNA strands mixed. Key thing to note that there are 4 endpoints. So one is TCA-CT, another one is TAGAG, another one is CATAC, another one is TCTTG. These 4 ends are known as sticky ends, consisting of just a branch of DNA, of ACGT. Okay, so each tile you can think of there are hands. Okay, and so each tile corresponds to, so basically tile corresponds to something like this. Another tile will correspond to something like this with ACGT value change. Right. Now two tile can come together if the corresponding hand are complementary. Okay, then they will join. Okay, so if, for example, if you look at second here molecule, this is double crossover molecule. So the value is AGAAC. So is it complementary there? Here? Where it is complementary? Anyone can tell? Out of these 4 here? Yeah, so this lower end and that upper end is complementary, right? So they will combine. Okay, so like that, these double crossover molecules, which are having sticky ends, will combine. So essentially, a tile something like this with the color matching business which we are talking about correspond to something like this in the hardware side, right? So now what happens? 2 of these tiles on the right hand side, if you observe, this black and black will match, so it will combine and give you something like this joint one, right? But there correspondingly ACG strings will match at the complementary, and then they will combine 2 DX molecules. Okay, so this is how the whole assembly will grow. Now, since everything is happening with respect to chemistry here, so there is a double crossover molecule, there is another double crossover molecule, 2 DX molecule will combine to give you an array, and then another DX molecule will combine, and another DX molecule will combine. So basically, there is a series of reactions that is happening, right? So there is certain forward rate of reaction and certain backward rate of reaction, because it's a chemistry altogether, right? So there is some forward rate of reaction and some backward rate of reaction. So something will combine, and something will happen, something may go off, and again it will grow like that. So all these things can be controlled by the certain thermodynamic parameters. So you can control the reaction. So essentially, you can control the DNA composition with bunch of thermodynamic controls, right? How to control the reaction. Okay, so you can control the forward rate of reaction and the backward rate of reaction, and they will determine the whole growth of the assembly, right? That is how this happens. So this is a very nice correlation. So you can see that these 2 DX molecules give you a bigger molecule, and the next one will come into picture. So the question is, if I ask you that you are a programmer who is going to program a DNA computer, what you should know? Obviously, you don't want to go into the hardware business, right? I mean, hardware means you go into the lab and then do the test tube things and so on. So Eric Winfree has devised this scheme that Given any mathematical or computational problem, if you can solve it by bunch of tiles, we are done. Okay. So you should know how to write a program in tile business. Okay. And also he has written a simulator. You can simulate and see exactly what happens in the computation process, right? Once you do the simulation, you are sure that now this is how it will work. Then you can design the experiments. You can actually, for each computational tiles and the frame tiles, you design the DNA molecules in the lab and do the computation. And they have done the computation successfully. The paper actually. Okay. So let me show you a little bit more details. So now I don't worry. I don't have to worry about the hardware. I know that whenever if I can show that something can be done with a bunch of tiles, we are safe, right? We can always do the hardware. Somebody else can do it. So this is a typical tile. Now remember, each tile has a free hand, sticky end of ACGT strings, right? So what is the strength of that string? You know, the bond that happens between them, right? So basically, there is something like this that we say that there is a tile and there is a so there are glues. You know, we are calling them glue. So this C glue, D glue, B glue, and A glue. And I can say that this some numerical quantification. We are saying that there is a strength. The strength of the glue here is 1, D is 1, B is 1, and A is 2. 2 strength. Some numerical quantification we are giving, right? So each tile when we are capturing. So what we are doing actually, we are approximating the whole chemical process in the form of tiles. It's a reasonably good approximation which will solve our problem, right? And you know, so that you can actually do certain things, right? So tiles correspond to the DNA molecules and the glue correspond to the sticky ends of the molecules. You see, these glues are of certain strength. Strength 1, strength 2, strength 3, and so on, right? So this is the whole capture of the thermodynamic whole reaction process, right? So these tiles are important for us. Now let me show you certain computations. So what is this model? This is known as tile assembly model, abstract tile assembly model. So just like there is a Turing machine model of a computation, there is a push-down automata model of a computation. There is now tile assembly model of the this DNA self-assembly process. Okay, why we call it DNA self-assembly? Because DNA has this tendency, if there are strings of opposite ACGT, right? So they will combine and form a bigger thing, right? So that is what is the key thing. So now let us see how this model works. So there are some assumptions here. So abstract tile assembly model. So a tiling model is an arrangement of different tiles that fit together perfectly in a plane, right? Tiles which will form a whole plane. So a tile system is a quadruple, capital T, right? Capital T is set of all tiles. S is a seed, G is the glue strength, and T is the temperature of the system. I mean, there is a way to actually capture this information from the thermodynamic process. How do you define? But in abstract sense, we are saying T is a number, an integer, which will determine what will happen to the tile business. And the label has non-negative strengths. For example, now if you look at this system here, this is a seed. So there is a blue tile, yellow tile, and these are connected. Okay. And here A3 is strength 1, A1 is strength 1. This is strength how much? 2. This is 1 and this is 1, right? The strength of the tile is given to us. Now there is a free tile which would like to combine here. So remember, in the Wang tile business, the color should match. So here the label should match. A2 should match to A2, A3 should match to A3, and so on. And the combined strength, right? So here, what happens? This A1 will combine with here. This A2 will combine with here. So this tile can attach. Provided, so one more condition is there, a tile can only attach itself to the assembly, that is the initial assembly, if the total strength of the label is greater than or equal to the system temperature T. So this system temperature I can predetermine. Normally in our computations, we take T is equal to 2. Okay. So now if you see, what is the combined strength here? 2 plus 2, 4, and 5 and 6. So combined glue distance is 6, which is bigger than 2. So this tile will attach. So two conditions one has to keep in mind. Number one, edges should match. A2, A2, A3, A3, A1, A1, all those things. Second, combined glue strength should be greater than or equal to the system temperature T. Then only a tile will attach to the assembly, right? So let me show you an example. Now you see, system temperature we have set 2, and there is a, this is the initial assembly consisting of 2 tiles, blue and green, and corresponding symbols are X, X, and V. This is V has strength 2, X has strength 1, X has strength 1, right? Now, suppose we have enough number of tiles of these tile types, this one, this one, this one. So like this has strength V is 2. Here actually there is no symbol attached, right? And no, so this is kind of 0. So nothing will happen from there. No computation will grow from here. Similarly here, okay? So these places, here also nothing will happen. Here also nothing will happen, okay? So they can combine. Now, so let us see how this will work. Can you guess which tile out of this can come here in the assembly? Out of those blue, green, or and red? Red will come because V will match, right? So now you see, red will come here. Now we have X and Y left, right? So which one can come here now? Green, right? Green. And remember, whenever we are combined glue strength is bigger than the temperature or equal to the temperature, right? That's what that condition is met. Label should match, and the the combined glue strength should be greater equal to the system temperature. This is how assembly will grow. Got it? Very basic. So now once you understood this molecular weighing tile system, the question is, if I ask you to do basic arithmetic like addition, subtraction, multiplication, division with these tile systems, can you do that? So you have to write a program. In fact, so our group has written a program by some of the BTech students earlier at DICT. They have written a program, X-Tile mod, which you can simulate. I mean, which you can actually calculate any expression, some sort of expression. And I think there was one girl, Tulsi Shah, who she went to Google, I guess. Some of you might be knowing her. She has written a DNA calci. I think we have not posted it here, but DNA calci. You just do the operations. The calculator will give. So GUI is there. You do the operations, and the output will be in the form of dot tiles, which you can simulate and see the behavior. Right. So once you have the dot tile files, I will show you what are the dot tile files. So that means you can send it to the simulator, see the behavior, everything is working fine. Then you can do the experiment actually. Okay. The beautiful result of Winfree. So Winfree use some of these objects known as DNA graphs, DNA complex graphs. I'm not going into too many details about how this was done, but for push down automata, certain kind of hardware is needed. For Turing machine, certain kind of hardware is needed. Okay, or for finite automata, certain kind of hardware is needed. So by changing the DNA hardware, right, you can and then you have to design an encoding mechanism. You have to map DNA hardware. So suppose you want to accept certain language. Okay, so then you have to design the appropriate DNA hardware and the encoding so that that language is accepted by the particular DNA, combination of the DNA molecules. Okay. So he has shown that self-assembly of linear duplex DNA into linear polymers produce regular languages. So what are linear duplex molecules, linear duplex DNA? As you can see that this one, the C, this is the duplex. So there is a duplex and there are some free strands, right? Okay. So this is the linear duplex. The A section is a Watson graph. Okay. So I'm not talking Watson-Crick subgraphs. This is a free strand. This is a hairpin. What women use, right? This is a hairpin. See that created by ACGT, right? And this is a 3-arm junction. There are 3 arms. You can see that all made by ACGT. And this is the double crossover molecule. The actual picture of the double crossover molecule. The slides which you saw, those things. And so there are 4 sticky ends. You can actually design. Okay. So each double crossover molecule has 4 sticky ends. Okay. So this is the basic hardware. So self-assembly of linear duplex DNA into linear polymers produces regular languages. Regular languages are accepted by finite automata, DFA, NFA. Self-assembly of duplexes, hairpins, and 3-arm junctions into dendrimers produces context-free languages. That is also taken care. Then self-assembly of double crossover molecules into 2-dimensional lattices achieves Turing universality, produce recursively enumerable languages. All the 3 main things, just by changing the DNA hardware, you can do the combination. Beautiful result, right? So that means now DNA you can control at the really nano scale. You can control the computation. And that means actually, that's why it is known as algorithmic self-assembly. Because now you can design algorithms for doing anything you want. Okay? You may ask, what are the applications? Now, a variety of applications. Once you get engineering at that precision level, you can design a, so for example, people have designed a box where you put a drug molecule and you can transport to the specific location in the body, right? That is a possibility. People have designed robots, molecular robots, walking at the nanoscale. All these experiments are done successfully. Okay, so people have designed ruler to measure distance between 2 molecules at the nanoscale. All kind of different applications are possible. Unless, if I talk about applications, probably 2-3 hours I can talk about that. There are so many things people have done. Okay, so that there are, but this shows you that the power mathematically, that now you can do anything. These are some of the listed problems I have listed. Using DNA self-assembly, you can do basic arithmetic, addition, subtraction, multiplication, division, and as I mentioned, your senior Tulsi Shah has designed the DNA calci. Finite field arithmetic, all that finite field business can be done by DNA self-assembly. People have done that also, right? So your favorite. Then path finding, in the 2-dimensional space, finding a path. That is also done. Boolean satisfiability problem. Fast Fourier transform, people have done with it. Okay. NTRU crypto system. What is the full form of NTRU? I think I have not covered NTRU, but it is number theory ring universe, right? It's one of the popular candidate for post-quantum cryptography. So if you know, many more. By the way, so of course I cannot show you all these problems, but I'm going to show you 2 specific toy problems to illustrate how this programming is done. Okay, so that you learn actually how to do the programming. Simple problem let us take, and let me give you an idea how this is done. So I'll first take binary counter. This is a binary counter. So what we want, you can see that the first row here is expansion of 0, binary expansion of 0. Next one is binary expansion of 1. Next one, binary expansion of 2, 3, 4, 5, and so on. This is a binary counter. I want to build this binary counter using this tile business. Any idea how should we approach? Now this is purely mathematical fun, right? As a programmer, you have to think. So you may be good at competitive programming, but here you may fail, right? How to do these programs to actually, we want to compute this. By the way, a very basic question. Suppose each bit here is the face value of a tile. So face value of a tile is each bit. How many tiles will be needed to compute this pattern? Any idea? And this is infinite binary counter. This keep on going. both the directions. You can count, 1, 2, 3, 4, 5, 6, 7, 8, keep on counting, right? Endless, infinite binary counter. How many tiles will be required? Any guess? At first glance, looks like infinite tiles will be required, right? Because for each face value, you should have one tile, right? But that's not the case. You can do this with minimum 4 tiles only. Whole pattern can be. So now here is the beauty. As a programmer, you should know which 4 tiles will do the job for you. Okay, which can give you the whole pattern. So let me show you those 4 tiles. So these are the 4 tiles. Okay. So base value 0, and you see that edge. Earlier we have taken A1, A2, A3 or color. So here we are representing by 0 or 1. Because what? 0 and 1 is 2 colors, I can say. Right. So I'm using 2 colors in the form of symbols I'm using, right? 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 0, 0, 1, 0, 1. And face value is important for me. Because face value is going to determine the whole shape of the counter. The question is, how do we determine that these things are going to work? So these are the colors. So for example, this tile and this tile, so 1 and 0 will not match. So it cannot come together, right? And we also assume that each color, 0 or 1, which is at the corner, is of strength 1. And the system temperature is T is equal to 2. Okay. So that means, how do we find out? So see, again, beauty. The beauty is here. So these are known as pad. So pad colors, and I can assume that, suppose this is the input and this is the input. So question is, suppose somebody gives you this solution and I ask you, is there a Boolean function, is there a function which can take these values and give us this value? Take 2 input and give you the output. So output is, these 2 are input and these 2 are output. Okay. So is there a function? You will be able to say yes. XOR and AND of these 2 things, right? You can check. Output one is XOR of 2 inputs, and if you do the AND, that's second output. So as a programmer, your job was to find this function so that you can find the color labeling, right? And now how this will solve the whole business, right? See how you can construct the whole thing. I hope you understood this function business, right? Now you see, in order to build this pattern, I wanted, so these 4 tiles are known as computational tiles. I also require 3 additional tiles known as, so one is seed tile and 2 are known as frame tiles, because you require certain frame to actually hold the whole pattern, right? So seed tile, this is S here, and then there are 2 frame, vertical and horizontal. Which one is horizontal? That 0. This is horizontal tile set, right? This one. You can see this is the horizontal tile set, and the other one is a vertical tile set. The vertical frame tile, and S is the seed. So somehow you need to bring this S, this 0, and this A together. Once this portion is formed, automatically this will attach, right? And so on. So you see how it happens. So if you see now, if I give initial concentration of S a little bit more, so chances of occurring the reaction will happen. And you see these tiles, so 0 will come because you see this symbol here, I am keeping this small rectangle, right? So S, there is a rectangle here and there is a rectangle here. The strength is 1, so they will combine, right? System temperature is 2, so this will grow in this direction. Nothing will grow in this side and this side because there is no function there, right? So this will grow in this direction. Similarly, this will grow in this direction. S, and then there is A will attach because this rectangle and this rectangle are same, right? They will combine and then grow. So this frame will be built first. Once the frame is built, so what is this value here? This value here is 0 and this value here is 1. Which tile out of these 4 tiles can come together? So here we need to see 0, 0. It cannot match. 0, 1. Yes, this will match, right? And this will not match. So 0, 1 can come here. And because system temperature is 2, each computational tile, the strength is 1. So combined glue strength is more than or equal to 2. So they will combine. So this tile will come here, right? Once this tile is done, then you know that this upper bit is 1 and this side bit is 1. So then which tile can come? Third one can come here, right? Like that, the whole process will grow. One by one tile will come. System temperature is you set to 2, and you see the whole thing growing. So the beauty is that only these 7 tiles can determine the whole pattern, right? 3 are the frame tiles. So essentially, you require only 4 computational tiles to generate this binary counter pattern. Now this is infinite counter. Suppose I ask you, I am giving you as an exercise, design a computational tile set which after user input, so user want to stop the computation counter say at 7 or say 10 user input. I am asking you a question as a programmer. Programmer input is I want to stop the computation in 11. Can you design those kind of tile set which will do the finite computation? So it is ceiling. I can give you a hint. You have to design the tile set that whatever user is giving you, that value you read, and then so of course it will be in the form of binary one-dimensional vector, right? And accordingly you seal the whole thing at that level. Actually, this has been solved. I am not giving you anything new, but whether you can become a good DNA computer programmer, so this is for you to as an exercise. It is not a competitive programming although, but I hope you will enjoy, right? How to stop it at a certain level, right? Okay. Now, here is a dot tile program which you can simulate on Eric Winfree. So how do we write this? So file name is dot tiles, anything you want, right? Binary counter dot tiles. Now you can see that there are this is seed tile, right? Do you agree? Because you see north, east, south, west, the values are this. So what is the value at north here? 1. East here, 0. It means nothing is there, right? And south, 0, nothing is there. And here it is 1. This is your seed tile. If you remember, seed tile. Something is here, right? On the east side and the north side, right? Similarly, now I think as I'm giving you an exercise, one of them is horizontal, one of them is vertical here, and these are all 4 computational tiles. Now, note that I am using colors 2 and 3. In this program, I am using color 2 and 3 to represent those 0 and 1. The edges were either 0 or 1, 2 colors. So whether you use that symbol as a 0 or 1 or whether you use that symbol 2 or 3, that is up to us, right? For example, if I take last tile, this will be what? North is 3, then east is what? 2, then south is 3, and this is 2. So which tile is this? And this face value comes here as a 3. So I think, let me show you which tile is from here. You can see that this bit and this bit are same, and this bit and this bit are same, right? Right? So which one is out of these 4? This is the case. Which one? So of course, either it is this, right? Because this bit and this bit is same, and this bit is same, right? Or maybe, of course, not the middle two, or this one, but this is the 0 1, right? So basically, this is here, all 0, right? So which is this? 2 2 2 2 is the same thing, right? This is the 0 1, 0 tile, because all 2 2 2 2 is there, right? 2 2 2 2 is this one, this one. Sorry, this one. So this tile is the one which we coded here. 2233 at the top. Got it? So basically here we are just, so you can, if you reduce it to mod 2, for example, you will get it. So 0 0 1 1 at the top, and the middle bit is 1, right? So I hope you got the idea how to convert, how to write a program. So essentially, you need to write this, either you do it manually. So now you understood how to do the computation. As a programmer, you have to write these .tile file to solve a problem. So we have developed the software uh, XTile mod for doing the arithmetic, or DNA Calci was developed by Tulsi, as I mentioned. In fact, first time when I gave this problem to 3 of your BTech students, so they have written the program XTile. XTile now has become the front end for DNA computing actually. Although now it is quite old, it's web-based, and we were developing a newer version, which is you can install. But so basically, our software can generate these dot tiles also. Just you give the logic, and dot tile file will be generated automatically. So let me show you. So there is a, so this is a simulator written by Eric Winfree. So you can see this is the home page. So they have mentioned about our group work XTile at Caltech. Okay. So uh, so there are now few more works by Jagro written by someone else, and then Jack has written a tool. And okay. And so this is a pretty old, I think 2009 or something when we did this. It's still, if you want a new version, we can release one, but of course it is at certain stage. So this is the page of XGrow simulator. So all these dot tile files you can simulate here. So these are the tarball which you can download and install. You will require a Linux machine or Apple system. On Windows, you have to again do the simulator and do all this business, right? You can do that. It requires a special X component. But anyway, let me show you. I think it might be live yet, or I'm not sure. Yeah, I'm not sure it will work now because it's very old. But let me try. This applet is not working. Oh, it is working maybe. Yeah, it's very old actually. So we have a better version with us, but so you can, I think the browser will probably not support, but anyway. Yeah, it's not working anyway. So we have a better version also, for this software was used to create dot tiles directly. Okay, so we have another version of it, but simulator you can download and run. So if you create dot tile file, or you can also, I would say, page. XTile mod. So here is a software which you can download. It's a Java file source. You can compile and you can actually do as an exercise for some of the arithmetic, say addition, subtraction, multiplication, division, and you can actually get the .tile file and you can simulate. This is all done by students here anyway. Okay, so similarly, if you want to compute this pattern, Sipranski triangle, you know, Pascal triangle mod 2. By the way, as an exercise, the Pascal triangle was known in India with what name? Okay, that you can figure it out. Now it is popularly known as Pascal triangle, but in India it was known as something else. If you really want to learn, you can look at the YouTube channel Shivoham. They have explained everything. What was there? Okay, Project Shivoham. Anyway, so so if you want to do this Pascal triangle mod 2, again you require 4 computational ties and 3 seed ties. Okay, so that is the thing. Once I said that you require 4 ties, you can also do it with certain other number of ties. So that is an optimization problem. How many tie sets are required to solve a computational problem? Right? It's a complexity issue, right? So for the counter, we have done a lot of things. But by the way, if you want to see the simulation of these things, look at lecture number 10 in IT 468 Natural Computing course, lecture number 10 simulation I have shown here. I cannot show it here because you require a laptop. I have to attach the laptop to show you the simulation, right? So you can actually see the simulation in lecture number 10, Natural Computing, Spring 2021 on our YouTube channel with something time around time stamp 15 minutes to 16 minutes or something like that. So, you know, or maybe 19 minutes, I guess. You can find out. I think 2-3 minutes ka to chalega, right? You can figure it out the simulation. I think, so here also, here is the .tile file for these colors. You can see that. Again, 7 tiles. So essentially, as a programmer, your job is to write down these tile file. So we have also the Shalin has computed computing real numbers with these tiles. How do you compute real numbers? So you have required tiles which will do the computation for you. You can compute square root, a lot of things. So DNA will do these things in the lab. Okay, so I will stop here. Next class I will cover few more things and then we'll talk about the more DNA cryptography.